Good morning. Good morning. Anup, is that you?
Yes, this is me.
Okay, good, good. I think we are ready to go. And so you will be in charge of this room, right? You will handle this video and
Right, right.
right. Okay.
So yesterday I tried playing the video and we had all the setup ready already.
Oh,
So
mhm.
it should be fine. We are expecting no hiccups. Okay.
Great.
But if
Thank you.
there's anything, I will contact you. But
Yeah,
hopefully that.
I will be in education class too, so I will be
Okay.
there. So,
Okay.
but I will be
Okay.
reading email if something comes up. Just feel free to let
Perfect.
me know. You can drop me an
Okay.
email.
Perfect.
Great. Thank
Thank you.
you. Okay, good.
I'm Marian.
Hello, can you hear me?
Yes, I can hear you. This is Anu.
Hi, Anoop. Is the
you're-
audio good enough?
Sorry?
I was asking whether the audio is of good enough quality because I have some extra microphones if needed.
Oh, yeah. The audio is very good.
Okay, okay.
So I also have Jan's video with me, so we'll play after your talk.
Yeah, yeah, I'll introduce it. Yeah.
Fantastic. And you can start whenever you're ready, okay?
Yeah, we have to wait for more people or?
Yeah, we can wait for another 5 minutes maybe, and then you can start.
Okay.
And usually what happens is students come in a little bit late and then.
Okay, okay. Yeah, I'll wait a few more minutes and then I'll get going. Okay, can you see my screen? Does that work? Can someone confirm either
Yes.
orally or in the chat? Yeah. Yes?
Yes, we can see.
Okay. So welcome. My name is Marjan Verelst. I am a professor at KU Leuven, so a university in Belgium, and my field is really machine learning, processor design, chip design. So in the next hour, I will talk a lot about that, and then we also have a part from Jan Rabai, but I'll explain next how our two lectures correspond to each other. The first hour will be with me. If you have any questions, just either raise your hand. I think I cannot that easily monitor the chat, but you can put something in there and then from time to time I'll take a look. You feel free to interrupt me. I will also from time to time stop and ask whether you have any questions, so then you can just speak up as well. So let's go. I don't know exactly what your background is, so always feel free to interrupt me if something is not clear. We can go any direction that's of interest to you. So what is my field of research is really to make extreme edge devices smart. And what is an extreme edge device is basically everything that's trying to make smart electronics, but in a very resource constrained scenario. So either you don't have a lot of battery power, you have to make something very low cost, there is not a lot of area, memory has to be pretty small. And this is what you typically find in things like wearables, implantables, drones, robots, cars, and so on. And the goal in my lab is really to make these things smart by themselves, what means that they should not send all their data to the cloud to get some responses back, but they should really be able to analyze themselves the data locally in the device using machine learning techniques. And this for latency reasons, privacy reasons, and also because if you do it well, it can be much more energy efficient. And that space is really called the tiny ML, or the field of tiny ML, tiny machine learning. And if you're working or interested in this field, I really encourage you to check out the Tiny ML organization. It is a big community of many people working in this space, both on the algorithmic side, on the hardware side, on the compiler side, on the application. So the TinyML community really brings together everyone across the stack active in this field and organizes weekly online talks. There is a research symposia. There is a yearly summit in US, one in Europe and one in Asia. The Asia one is coming up. So feel free to explore more if that interests you. Now, what is the challenge of TinyML? It's really big that we have to bring together on one hand the machine learning side, where there is a wide variety of different machine learning techniques and models, from simple decision trees to the very popular neural networks to more exotic things like hyperdimensional computing and everything in between. And that you want to do on an embedded system where you have very tough constraints, both in terms of latency and energy consumption, and in terms of your cost, and then resulting in area and memory constraints. And TinyML has to bring together these two worlds. And that's really what I want to talk to you about this lecture. And I'm a hardware designer, a circuit designer, so we're going to look at it from the silicon point of view. But you're going to, even if you're an algorithmic designer or a scheduler, compiler person, you're going to get a lot of insights from seeing the constraints that come from the hardware. As you have heard, we are teaching this with two people. My name is Marjan Verhelst, but my colleague Jan Rabai will take care of the second hour. And how we organize this is basically that I will be lecturing, let me get a pointer. I will be lecturing about running deep neural networks in embedded resource constrained devices. And Jan Rabai will focus on doing hyperdimensional computing, a more upcoming emerging flavor of machine learning, while these neural nets obviously start to be well established. So the first hour with me on part 1, second hour with Jan on part 2. Unfortunately, Jan Rabai has booked a flight during his lecture time because he mixed up the times. So his lecture is recorded and will be played after my first part. So let's get going with the neural networks. You would think that neural nets are already basically everywhere in our devices, that we don't have to do anything special for them anymore because you already have them in, on one hand, your phones to do the face unlock, and in your phones to do the speech detection, and in your cars to do lane assist, or in your glasses, if you already have some of the more fancy glasses that can do some detection of objects around you and so on. But the problem is that this is not really the advanced machine learning we are dreaming of. Yes, there is neural nets everywhere, but there are still very small networks doing rather simple tasks and not even running everything embedded, because a lot of data is still sent to the cloud. And if you have these cool VR glasses or some AR glasses, then they're either very bulky or they have limited battery lifetime. So it's clear we're not fully there yet where we want to be. And the question is, what is the gap? What can we do today? And what would we like to be able to do from a hardware algorithm point of view? And I took for that 2 applications of my previous slide. On the left, we have the smart car application. And let's start with that. I'm going to take some extremely naive assumptions. I'm going to assume that I only need 6 cameras, full HD cameras at 30 frames per second. But let's do it 6. The real smart car probably wants a bit more, but okay. I'm going to assume that I have to do one ResNet 50 network. This is a type of or one neural network model that I'm going to evaluate that on every frame of the camera. I cannot do full self-driving with this ResNet 50 network. Obviously, it's a rather simple network, but let's just set a lower bound. This is an underestimation of the amount of work I have to do. And I have to do that in a 10-watt power budget. And 10 watt is exactly the amount of power you can, or roughly the amount of power you can cool in the glove compartment of your car, which is where typically these application processors are put right behind the glove compartment. So if you do the math on all these input data, it turns out that you have to do about 300 giga, so 300 billion operations per second for every image frame, resulting in a throughput need of about 100 tera operations per second. So 10 to the power 14 in total operations per second. And in a 10 watt power budget, so I have to do 10 tera operations per second per watt of power I invest. This is an energy efficiency metric that we get here, a throughput metric and an energy efficiency metric. If I now look at the smart glass application, obviously there I do not need 6 cameras. Maybe I'm happy with a stereo camera and some eye tracking camera. I still naively assume I run a ResNet 50 on every frame, but now I only have a 100 milliwatt power budget because, yeah, it's not a car with a lot of storage capabilities. It's just a small glass. So if you again do the math, you see your throughput requirement becomes a bit less, 10 tops per second, but I now need an energy efficiency of about 100 tera operations per second per watt. Okay, these are numbers, but is this a lot? Is this not very much? What can we do today? Well, again, let's take a look. So here on the x-axis, you see power consumption. On the y-axis, you see throughput, giga operations per second. And the diagonal lines you see here, they are hence energy efficiency, so operations per second per watt. And our 2 applications of previous slides are depicted here. And now every single dot you will see in this slide is one different chip, one different hardware platform. So all the green dots are different GPUs. On the one hand, you see some high-end GPUs, and as you can see, they meet the throughput requirements we have, but they're consuming too much power. On the other hand, you have some more power efficient embedded GPUs, but they don't have the throughputs that we need. So GPU doesn't bring us yet to where we want to be. You could say, okay, let's implement on an FPGA, a reprogrammable hardware platform. But as you can see here, it doesn't bring you much, at least not for energy efficiency or throughput. An FPGA is not a super efficient platform. It's very flexible, too flexible almost. But then the whole field, the neural network processing field, is flooded recently with a lot of application-specific processors. So every dot here, both the purple, which are digital chips, and the orange, these are mixed signal chips. Every of these dots is a different research or commercial chips holding a processor optimized for neural network processor execution. So really customized with a separate instruction set to run neural networks more efficiently. And you see that they start to get, we're not fully there yet, but they start to get close to my naive underestimations of what I want for my embedded system. Several of the chips in this graph are from my lab. And in this presentation, I'll talk a bit more about this one here, which is the Diana chip, but that will come more towards the end. Now, what I want you to learn in the lesson today is how do all these dots, how do all the purple and the orange dots, how do they do better than these GPUs or the lonely CPU here in the bottom? And it turns out they're mainly exploiting 2 tricks. They're going to be smart in terms of supported precisions, but okay, some GPUs and CPUs can do that too. But especially they're going to play on the data flow of the processor. And I'll explain you what that means. Then we're going to look into one specific chip from my lab, and then we're going to talk a bit about scheduling and design space exploration. So first of all, to understand why all these chips can do so much better than a GPU or a CPU, we have to understand the workload of a neural network. And I'm simplifying it a bit here, but the main workhorse of the neural network executions are matrix multiplications. So I have a matrix of inputs, I have a matrix of weights, and I have to multiply them to get a weight matrix of outputs. And so every row of the input is multiplied with columns of the weights, and every column of the weights is multiplied with the row of the inputs to get these outputs here. And every neural network processor, and there's many dots in my previous slides, but they all inherently look alike or have the same base architecture. They all contain an array of processing elements, PEs. And every processing element holds typically a multiply or one or more multiply accumulate blocks. I have to do a multiplication of the blue and the red elements and I have to add them all up across a row to get, or column, to get a single output. And so this is preceded by some registers to store data locally, and also at the output I can store some results for the accumulation here. Of course, these processing elements have to get their data from somewhere, so they're typically fed by an on-chip memory system with one or more levels of SRAM and register files. So where you can locally cache either weights or inputs or outputs to not constantly have to fetch them from a larger off-chip storage where your input might be residing and definitely your weights are typically residing. Now, if I now want to execute this matrix multiplication, what do I have to do? Well, I have to, first of all, bring my inputs and my weights from my off-chip storage, my DRAM, into my chip, my processor chip. Then I have to bring the data from here into the processing elements. And then I can do my multiply accumulate. Now, this is the actual operation I want to do. It will cost me some energy, but it's energy I'm happy to spend. But we shouldn't forget that bringing the data on chip and bringing it from the on-chip memory through the hierarchy of the memories into the data path also costs me energy. And if I have my result here, writing it back from here to here into my off-chip storage to do later computations in the rest of the network also costs me energy. So if you really want to make a very efficient embedded system that runs neural networks, it means you have to optimize across all these different aspects of the neural network execution. And if you look a bit at the typical processors in the field, if you don't optimize it properly, you will just be spending most of your energy on this DRAM interface here. And then the SRAM accesses will also cost me quite a bit. And the compute itself, at least as at the start, if you don't do some smart tricks, is just a tiny fraction of the whole energy consumption. So what do people now do to make this more efficient, to at least spend more of my energy on compute and hence shrink the yellow and the green part of my power consumption pie chart? That's the trick that CPUs cannot do that easily, where GPUs, but definitely these neural processors, start to become better at. Well, they play a couple tricks. The first thing, obviously, you want to do is keep this I/O transfer as low as possible. And people do that by integrating more and more memory on chip. And having a memory of several megabytes is no exception, because I want to store as many weights as possible in my chip, because then they don't have to come from off chip. Or if it's possible, and it depends a bit on the network, but if you can store the output of one layer fully in your on-chip memory, and it doesn't have to go back to off-chip, and it can be directly fed as the input of the next layer without going through the DRAM, but directly from the SRAM back into my data path. That can save you a lot of power. So this output to input feeding without going off chip is one important one. The other one, as I said, is storing the red matrix, my weights on chip. And if they're too big, there are tricks to make it smaller. We're not going to go in detail onto this in this presentation, but you can compress the network weights by playing some sparsity tricks. You can try to build more elegant models by building things out of depth-wise, point-wise layers instead of conv3D layers, and that will also reduce the amount of data in your weight model memory. Now, if you can do these algorithmic tricks to bring this energy down, the next sorrows, of course, are in the parts here. And there, the first trick to play is to critically wonder what precision you want your AI algorithm, your neural network, to be executed at. Do I really need floating point operations, 32-bit floating point, to execute my networks? The answer is no. Many neural network inference can get away, or almost all of them, with 8-bit integer operations. Some of them can even go down to 4 bits or lower. And obviously, if I can compute at less bits, if I can do 4-bit computation of my neural network layer, well, then I save across all these elements of my power consumption formula, because now I only have to bring 4 bits or 8-bit data on chip. So this will go down. I only have to fetch 4-bit data or 8-bit data from my SRAM. So this will go down linearly with my precision. And I now don't have to do a 32-bit or a floating point computation, but just a low precision integer computation in my multiply accumulate. And this will even super linearly save you power, typically to the power 1.5 of the precision savings that you have. So that's a very hot field, both in the algorithmic as well as in the hardware community, to try on one hand to build processors that support different precision levels, and on the other hand, to make algorithms operate at, or to train the neural networks to operate at the lowest precision possible. And what people start to realize is that not every layer of the neural network needs the same precision. Definitely, some tasks need a higher precision than others, but even within one neural network for one task, there are layers that can get away with lower precision networks or lower precision computations than others. What people now try to do is train neural nets, as you see here, which for every layer, so every bar is a different layer, uses a different precision for activations and a different precision for weights. So this is for ResNet 50, the network I talked about earlier, in total having 50 some layers. Well, it turns out some layers can get away with a 1-bit weight and 3-bit activations, and other layers maybe, let's see here at the end, need 4-bit weights, and in this case also 3-bit activations. So the number of, or the precision you need in every layer is different. And how people do that is they train the neural network, but they train it for different alternatives for every layer. So this is layer 1, and I make a 1-bit alternative, a 2-bit, an n-bit, and so on. For layer 2, the same, and so on. You start to train the network, and now my precision becomes differentiable. So whether I take this path or this path or this path is differentiable, because in the beginning I take them all. I have a summation sign here, and the weights in the beginning are still across all the arrows or rather equal. And now these weights pi, they're also training parameters of your network. And over time, the network will start to strengthen one of the paths, maybe here the 1-bit path and here the 4-bit path. One path gets strengthened and the other gets suppressed. And using some Gumbel softmax function, at the end of your training, one path will be dominant for each layer, and then you know at what precision that layer has to run. This is another example, the inception tree network. You see also some layers need a lot of precision, and others can get away with really low precision. So if you want to hear more about it, this paper explains that in more detail. And it becomes clear I now need processors that can both operate at 1-bit, at 2-bit, at 4-bit, maybe at 8-bit for some networks. This needs special hardware support. One chip that already did that is a chip from my lab in 2017, where you see here that we had processing elements that could each do int16 computations, but they had a small configuration register that allowed them to be reprogrammed to either do 2 8-bit computations in parallel, 4 4-bit computations in parallel, or even parallel 2-bit computations and so on. So you could reprogram every processing element to operate in different precision modes. In more recent chips and even in GPUs nowadays, this is becoming kind of standard. It was a bit new in 2017, but I have this annoying bar at the top. It was a bit new in 2017, but now this is, for example, one of IBM's chips where they have an int4 data path, an int2 data path, a floating point 8, a floating point 16 data path. Or NVIDIA's Tensor cores, now they all can operate in both floating point and int modes, and then across different precision levels. That was the first trick every neural processor uses. Second trick every neural processor uses is to play with the data flow of your processor, and this to have as much data reuse as possible. What does this mean? Well, remember that this yellow part here was pretty dominant, that the energy I need to get data in and out of these registers, of these SRAM memories on my chip. But we also remember that I explained you that every row here of this vector I has to be multiplied with every column of the weight to get my different outputs here. But also every column of my weight is multiplied with every row of the vector or of the matrix I here to get my different outputs on the vertical dimension. So the result is that if I fetch a data element, whether it's this one or that one, I do not want to use it once. I can use the same data element in many multiplications. And if I can do that at once, I don't have to constantly fetch from my SRAM. I fetch the data element once and I apply it to multiple processing elements in parallel. I'm going to do reuse of my data. And this data reuse is very important because now my energy of this read-write drops by a significant factor, and my reuse factor. And this can really save you up to a factor 10, at least in energy consumption of this data interface, this memory interface. Because I fetch my weight once, I apply to many multipliers. I fetch my input once, I apply to many multipliers for this horizontal dimension here. And my output here, I can accumulate again over many PEs before sending it back into my memory. So this data reuse is extremely important. And it's typically done in neural network processors, like you can see here at the MAC array, by doing some accumulation or reuse across one dimension as well as across the other dimension. And we then typically, if you look at a typical neural network processor, this is a naive matrix multiplication. In more realistic convolutional networks, you have a bit more dimensions, and you can write it as nested for loops for the X dimension of my output, for the Y dimension of my outputs across the channels, the output channels, input channels, and so on. Well, what you will do if you're doing this data reuse is that you will do spatial unrolling parallel some of these for loops. So we call them par for. So for example, if I have my output channels unrolled across the columns or the one row of my multiply accumulate processing elements, then I'm basically doing the reuse of my input data across all these multiply accumulates, because they all represent a different output channel that is doing operations on the same input. And if I do a par for, so a spatial unrolling, a parallelization of my C loop, well, my C loop is where I do my accumulation. That is basically this horizontal and this vertical dimension where you accumulate to a single output. Well, across the C loop, the parallelization allows reuse of my outputs before they go back to memory. So by playing with these par for loops, what do you spatially unroll? What do you do in parallel in your data path? You can save a lot of your energy of the memory. And the rest of your loops, the rest of the computations is then temporally unrolled. And also in this temporal unrolling, you can save, because by ordering these for loops well, I can determine what data is stored in my SRAM and when it has to be replenished from DRAM. So you can play a bit with which loop is served by which memory level. If this interests you and is a bit complex, then at the end I can point you to some papers that explain this in much more detail. Now, why do I explain this so step by step? Because this data reuse will have a strong impact on the performance of your processor. And this, or the challenge here comes from the fact that not all neural network layers have the same dimension. As simply said, these matrices across different neural layers will not always have the same shape. Some will be long and not very high. Others will be very high, but only shallow in the other dimension. And the result is that if I unroll some of these dimensions, if I will unroll some of these X and Y dimensions of my matrix or my tensor here on my data path, well, sometimes it might be that I maybe have 16 elements in one column, but I only have 8 elements in my actual operations I have to do that I can unroll on there. And then half of my data path, half of my processing elements will be idle, not doing anything useful, wasting energy, wasting the clock cycle. Of course, if I have a data path that's so flexible that I don't only support this kind of spatial unrolling, parallelization, but I also support other kind of combinations, and maybe I will now unroll 16 of this K dimension, 8 of this Y dimension, or sorry, 2 of this Y dimension and 8 of the X, then all my processing elements are busy again. With my hardware and my scheduler, my compiler, now have to support two different ways of doing the spatial unrolling, of doing the parallelization. And again, not all processors support that. Not all compilers are smart enough for this. Again, a link to a chip made in my lab 2 years ago, where we had a huge data path, 128 processing elements with a multiply accumulate in one row, 16 of these rows. So in total, 2048 processing elements. And if you would just always use them in the same way with the same parallelization, the same temporal loops, not all neural network layers can optimally fill these 2000 operations every clock cycle. But the chip was made such that it could operate in many different data flow and unrolling modes. And as a result, it had a very efficient utilization. A very high percentage of the processing elements were used across many different types of neural network layers, across conv3D, pointwise layers, depthwise layers, and so on and so on. Another example from other people at HPCA, where what they did there is say, no, we're not going to make our processing array very flexible. We'll just put many different processing arrays next to each other. And one has one type of spatial unrolling and parallelization. Another one has another type of parallelization, and this one yet another. And depending on my layer, I will execute a layer on this one, or on that one, or on that one. So the scheduler and the compiler will send the layer to the right hardware accelerator, the right processor, you could say. But then some of them are idle, of course. But again, there is tricks for that. We'll come to that a bit later. So a last thing I want to mention here in this part, before I'll leave some time for some questions, is a recent trend that becomes very popular that tries to combine trick 1 and 2. So I want to have very flexible and low precision compute with a data path with a lot of data reuse. And this is compute in memory. So what we're trying to do here is use a normal memory, an SRAM, to do very efficient compute. And how that works is, in my normal SRAM memory cells, I'm going to store my weights and different elements of my weights, one column here, one column here, one column here, and so on. And now I'm going to apply my inputs to the different word lines of the memory. And you have to binarize them then, or do some other multi-level tricks. It's out of scope of this little lecture, but you apply them here, and this SRAM cell will now operate, oops, yeah, it's not here. The SRAM cell will now operate as a small multiplier that multiplies the weight in here with this bit word line, because only if this one is 1 and this one is 1, a 1 will come out of the memory. And then this will be a small current or charge injected into the bit line of my SRAM memory. And if all these current and charges are injected across a whole column here, then I automatically have an analog accumulation on this bit line. I'm accumulating my current or charges. And that results in extremely efficient computation. So this analog compute in memory, because the addition, the expensive addition is done in the analog domain, allows you to process super efficiently at very high operations per second per watt. There's only one downside here, or one important downside, is that I kind of have to hope that my neural network layer nicely has the shape of my memory, because suppose I have 500 cells in a row and 500 cells in any column. Well, if my neural network matrices are smaller, again, I will have many idle cells. And adding more flexibility in this data path, like I just did in my digital chip, is very hard here, because this memory, the SRAM cells are tightly abutted. You cannot easily insert some multiplexers or smart switches in between. So this thing is very efficient, but only if you use the complete array well, which in practice turns out to sometimes be a bit difficult. So there we are a bit at the end of this first part, where you see now already the tricks that all these orange and purple dots are playing to get as close as possible to this ideal corner here on the top. But with this caveat or warning that they're all very good in peak performance when the full array is used and everything is nicely using low precision and so on. Actual neural nets which needs varieties of precision and which have very different shapes for rows and columns of their tensors, typically don't do as good as where these guys add the numbers put in the papers, because they are reporting the peak performance, not the actual neural workload performance. Yeah. So let's maybe break here to see whether there's any questions already. You can either put them in the chat or you can raise your hand. Let me monitor the chat a bit. Not yet, or feel free to speak up. We're not that many people apparently. Okay, so let's continue. What you then saw is that, yes, I like to use these very efficient accelerators with a lot of data reuse and low precision. And typically, especially the middle of the neural networks can go with this low precision. If I go back to my example here, typically in the middle, you have quite a few layers with low precision. They have a large size. They would be perfect on this kind of in-memory computer arrays that we saw here. But if you look more to the first layers and the last layers of the network, typically you need quite higher precision there. And there is typically also a bit weird shapes, either few input channels or very small tensor XY dimensions at the end. They're not efficient on these big computing memory accelerators. They're never gonna run with a very high performance there. On top of it, I need to do some pre-processing on my image, maybe some post-processing, and these accelerators definitely don't have the flexibility to do all of that. So what we want is kind of a system that can do it all, that has efficient in-memory compute for the middle layers where you want to run very large tensors at very low precision, but also have other accelerators, other data paths that can really efficiently execute these layers that need more precision, that have weird shapes, and so on and so on. So that's a bit what drives people to build heterogeneous systems. Already a bit what you saw in the example I give here on the right, where I'm not going to put a single accelerator, but maybe we'll put multiple accelerators. And this is not new in the neural network field, it's new. But we're used to this because all the phones we have in our pockets, they're very heterogeneous, combining CPUs and GPUs and neural processors. What you see here on the right is the Tesla full self-driving chips. And again, we see video processors, image signal processors, GPUs, CPUs, and neural processors. So already very heterogeneous systems on a chip start to pop up. But all of these are not really extreme edge, super low power systems. They still consume multiple watts in their execution. And the question is, can we also bring this kind of idea to the extreme edge, make them extremely low power? And here an interesting chip to look at is the GAP9 from Brainwaves. It's a chip with many CPU cores, 8 of them, as you can see here, and then some fabric controller on the side. And then one HWCE. This is a neural network processor or optimized accelerator, but it's only one. So the system, it's low power, super low power, but not that heterogeneous yet. It cannot support that many different data flows and so on, and it's very CPU heavy. So that's a bit what the Diana system tried to overcome. What we did in this Diana system is really try to make a system that can both do this very efficient, high throughput, low precision in memory compute, but also on the other hand, do all the necessary tasks that only a CPU can do, and the normal digital AI acceleration for these middle layers. So the system co-integrates the CPU for pre-processing, post-processing, very flexible. A digital AI core, which is flexible in terms of having shallow layers or deep layers, fully connected layers, high precision, low precision, and so on. And then this in-memory compute block, which is good at low precision, massive tensor, large tensor operation. And altogether, it looks a bit like this, CPU on a bus with a shared memory with a digital AI core and an analog AI core. And these cores are really optimized for very different things. The digital AI core is optimized for flexibility. It's flexible in terms of precision, can compute at 2-bit, 4-bit, 8-bit precision. It's flexible in terms of data flows to efficiently map different neural network layers, convolutional, fully connected, and so on and so on. And it's flexible in terms of whether the X or the K dimensions are unrolled, the K or the C, so it can do different kind of spatial unrollings on the core. On the other hand, so this is the green core. On the other hand, this red core, the analog core, is really optimized for efficiency. So it's not flexible at all. It's just highly energy and throughput efficient. So it has 1,152 rows, and it has 512 columns. So it's really a system with in total 500,000 multiply accumulates, 500,000 memory cells that do a multiply accumulate operation, super high throughput, but only at 6-bit input accuracy and ternary weight, so 1.5-bit weights, so at low precision. And the system is fully optimized to do very efficient processing. And for example, fully pipelines on one hand, fetching data for the next compute cycle, doing the compute in the in-memory block, and doing the post-processing of activation functions, normalization, requantization, and so on. So this is a fully pipelined system to make this 500 million multiply accumulates busy every single clock cycle. So not flexible, highly efficient. And in the Diana system, they're now combined. So on one hand, my digital subsystem can operate across all these different precisions and has an efficiency, if you take the nominal supply voltage, of about 2 tera operations per second per watt at a throughput of about 200 giga operations per second. While this analog core operating at lower precision, so it's not an apples and apples comparison. Now this one can operate at a bit more than 200 tera operations per second per watt at a throughput of 17-ish tera operations per second. So the difference between the two of them is a factor 100. A factor 100 both in throughput and a factor 100 in energy efficiency. So how do you now exploit that? Well, they have to go look at how to schedule actual workloads on there for maximum efficiency. So we have the core, or the 3 different cores integrated in a single system. And we now have neural networks where we want to understand that maybe it's best to run layer 0 that needs a high precision on the digital core, maybe some middle layers that can get away with low precision on the analog core, and maybe the last fully connected layer that's not efficient on an analog core back in the digital domain. Now the question is, how can we make this kind of operation and make sure these digital and analog core can very efficiently exchange data? And how can we decide which layer to run where and schedule this effectively and see what the best distribution is? And why not layer 1 also in digital? So how do we find the best layer to core allocation? Basically, that's the second part that I want to discuss. But first, how do these cores share data? Let me first also check the questions, whether you have any question that I should go through. Don't feel shy to ask questions. I'm here for you. It's a live lecture, so you can exploit it. Okay, so how do they share data? If I run layer 0 on the digital core and layer 1 on the analog core, how does this analog core get this data? Well, for that, you have to realize that the 2 cores have a shared memory. If I go a bit back, I can also show it here. Sorry. Yeah, top level. So you see you have the digital core, the analog, they're both on the same XE-APB bus and have a shared level 2 memory, but that's pretty expensive access. This bus is not that fast, doesn't have that high bandwidth. But on top of it, these 2 cores have the same level 1 cache. It's a scratch pad, basically at the lowest level, tightly integrated with their compute, that they both share. They both have read and write ports into this memory. And this is exactly what is going to be exploited here to do the data exchange between the 2 cores. So they're going to compute 1 layer on the digital core, is going to save the output in the level 1 sketchpad, and the analog core can fetch it back to execute layer 2 and layer 3 of the network. The only problem is that this output is quite large. And if this output is very large, it might not completely fit in this level 1 memory. That would be a big problem. Then it has to go to the level 2 cache, and it's slow and it's energy expensive and so on. Second problem I see when I sketch this out is that the analog core is idle for so long, and here the digital core is idle. What a waste that this one is computing and this one's doing nothing. And then this one is computing, this one's doing nothing. That's completely ruining my utilization of my compute array. But luckily we can do something about it. Because if you have doing a convolutional neural network, you have quite localized compute, you could chop your inputs into different sub-blocks. Let's say 1/3 is block 1A, block 1B, block 1C. And if one of these blocks is already ready with computing, that data can already be sent to the analog core to start the computation of the second layer with that data and the third layer. And while that computation is going on, this first layer can already continue with the next chop at the next block of data so that it can later be sent to. And now we have two benefits. On one hand, the cores are now operating in parallel and the idle time is much less. So I'm done more quickly with my compute. My throughput goes up. The other hand, the amount of data that has to be transferred here is much smaller than the one that has to be transferred here. So I can get away with a smaller memory. And if we do the math on an actual network, a ResNet 18 network, it's another neural network model. What we can see is if we do the computation without the chopping of the layers, so we, on the left part, if we do this pipelining only computation, you see you are executing in 6 milliseconds the whole network, and you need about 900 kilobytes of memory to store data from the output of this layer to the input of the analog core. But my level 1 cache is not about 900 kilobytes. Even my level 2 cache is only 500 kilobytes. This would have to go to offsite DRAM, which would be a disaster. If we do this chopping of the neural net into 8 parts in this case, then you see you're executing 40% faster, and we only need 200 kilobytes of memory. So we can now nicely fit into the level 1 memory. Saves us a lot of energy, a lot of throughput. So this is called layer fusion. We're fusing the scheduling of different neural network layers. Now the problem is, of course, if I start to do layer fusion and all these layers are computed in parallel, it starts to become very complex to basically figure out what has to be executed where, on what core, where does the data go, and so on. So for that, we have built a tool that basically allows us to aid in this scheduling. So at the core of this tool, and it's called Zigzag, it's fully open source. You can download it here or play with it. There are lots of tutorials and YouTube videos on how to use it and so on. So everyone's more than welcome to explore this. At the core of this tool, the Zigzag tool, there is a cost model. The cost model tries to predict if I have this neural network layer on this kind of hardware, a processor with so much bandwidth and so many levels of memory and this size of the data path with this kind of data flows and so on, in a certain technology, how much energy will it cost me to execute this neural net on that core? How much latency will it take? And what's the area of the chip? Of course, there is not one way to map a workload on a core. You can map neural nets on a core in many different ways. As I said, with different parallelizations, different order of my temporal loop. So this system will try all possible mappings that are supported by the hardware, where the data flow is available in the hardware, and will basically find Pareto curves. Every different dot is a different schedule. It will find the Pareto curve, and maybe you can now pick the most energy efficient solution or the most latency efficient solution, whatever you need. Yeah, this is just a validation to show that the models are fairly accurate against silicon that we have in the lab. Once you have this, you can, of course, now use it to take a neural net and map it on a single core system, layer by layer executed. But I can now also use it to take a neural network and map it on a multi-core system and decide that layer 0 is more efficiently executed on core 0, but layer 1 on core 1 and layer 4 maybe also, and make a schedule of my execution across my different cores. And this is still without a layer fusion, just in the pipeline manner. But the tool also allows now to chop every layer into multiple pieces, like layer 0 is in 2 pieces and layer 1 and so on. And now schedule this chopped, the layer fused network, either on a single core or on multi-core, as you see here, what we also did for Diana. And once you can do that, you can really use it to optimize your execution. Let me show this first. To optimize your execution, for example, of this ResNet on the Diana system. So again, you have the Diana system with the CPU, the digital AI core, the analog AI core. And what Zigzag now says is that you have to run layer 0 on the digital core in many chopped up pieces. So as soon as one piece is done, the analog core starts to execute layer 2, layer 3, and so on the analog core. And then the SIMD core is executing layer 5, and so on and so on. So it really shows across time who is executing what. And this allows us to make memory traces. How much is the memory used of each of the cores across clock cycles? And hence in total, how many clock cycles will my execution be layer by layer versus layer fused? And you again see what I showed earlier, this 40% less execution time and this 7x drop in memory usage of my system. As you see, maybe sometimes I'm interested to push my execution time more. Maybe sometimes I'm more memory constrained. So this optimization tool, the scheduler in this tool, allows also to explore for both. So you can either say, give me the lowest latency schedule, and you see that he then squeezes everything together, but it might need some more storage because I have to take the data of multiple layers and store them in parallel. Or you say, no, give me the schedule with the lowest memory footprint that doesn't use a lot of memory on my chip. And then he spreads out compute a bit more. It takes a bit more clock cycles, but it uses, in this case, a factor of 2 less memory, which could be good for more memory constrained systems. So this is a matter of the cost function of the optimizer in this scheduler. Voilà, so more details. As I said, this multi-core system is also published separately and is also available. It's called Stream. The multi-core extension to Zigzag is Stream, and it's also available open source on our GitHub of the research group. Once you have this, there is a last interesting twist you can start to do, and this you don't only can play with the schedule, but in my tool, in my models, I can also play with my hardware architecture. And I can use exactly the same tool again to now iterate over different processors with more memory, less memory, larger computer arrays, smaller computer arrays, more cores, less cores, to see what the impact is on the efficiency of multiple neural network workloads, for example. Now, without going into a lot of details, you see here an exploration we did like that to figure out how much memory we would want in the Diana architecture and what the size of the computing memory array we want. That is 1152 rows and the 512 columns. How to find the best trade-off between throughput per unit area and energy efficiency. And then it depends, of course, on which networks you favor and so on. Or you can say, no, given that I have a certain amount of silicon area, area, for example, for 1,000 processing elements and 2 megabytes of memory, do I rather want to make a single core system with a large array and 2 big memories? Or do I want to make a quad core system with smaller memories and smaller computer arrays, taking the same total area as the left one? Or do I want to take a quad-core system with, again, the same area, the same memory size in total, but where every core has different data flows? What's the most efficient for a certain group of networks? And this is a study we did across different networks, we're still working on the study, in fact, and where you see that all these different options, so the first 3 SC or single core options, the MC, the first 3 are multi-core options, but each with a different data flow. And the last one is the multi-core heterogeneous data flow. And that we did across different networks. And we checked the energy delay product of running the network on that core, both in the pipeline fashion, so without layer fusion, and in the layer fused fashion. What you typically see, and this is the geometric mean of all workloads, is that you get the best efficiency with heterogeneous systems where different data flows are present, and with this streaming and with this layer fusion, fine-grained layer fusion. This study we're continuing, and there is already a prelim version on arXiv, but the more final paper will come out later. What can you already learn from it? That you really have to optimize this data movement between cores. So the scheduler and the quality of the scheduler is very important. That your memory bandwidths are crucial to the throughput of your system. Even more important, I would almost say, than the size of the processing array. And that this active loading and unloading of data is very dominant in the total power consumption. So that's really, having efficient memories is more important than having an efficient multiplier, basically. Voila. That brings me to the end of what I had prepared. And as I said, we can still have a discussion afterwards. But my main conclusions is these optimized processors for neural nets. They are very important in the sense that they bring us large additional gains. But you have to be careful to not make them too specific, too specialized, customized to a certain network or layer type, because you really, to get efficiency, you have to support multiple precision levels, multiple data flows. So the field is really moving into heterogeneous AI accelerators that have multiple cores, now still mostly homogeneous multi-core, but more and more also, I believe, we will see this heterogeneous multi-core system. This requires very tight optimization between scheduling, compilation, data flows, hardware design, for which you need tools like Zigzag and Stream to do these system level explorations, this hardware aware scheduling, and so on. That's so important in this field. Voila, that's what I had prepared, and I'm open to any question or discussion or comment or whatever you guys want to do. You can just speak up, or if you're shy, type it in the chat. No question? Oh, yes, there is one. Okay, let me read it. So, first question, 2 cores with different precision, does this impact inference accuracy in any way? Is there accuracy performance trade-off? So definitely, if you play with the precision of the network, it can have precision impacts. So there is basically is the role of the algorithm designer to make sure that this precision is okay for the network. Like, for example, here, the networks are trained with the knowledge of the precision. So it's not that you take a neural net and then just reduce the precision. That would not work. You have to train the neural network, or at least fine-tune it to work at certain precision levels. But if you do that well, typically precision can be squeezed quite a lot to these resonant numbers you see here without accuracy losses. But you have to do it in training, or at least with some training, fine-tuning steps afterwards. If you just would cut the precision, definitely accuracy loss would be there. Now, even if you do it in training, there is a nice trade-off indeed, that I can push accuracy even further, but it will start to hurt me in total accuracy. And then people can play with that, to squeeze here a bit more bits off here, but then maybe have 1% less in recognition accuracy. I think that was the first question. Second question, state-of-the-art vision models use transformer architecture. Can Diana and Zigzag support transformers? And do we expect the same performance improvement for transformers as ConfNet? So Diana is a chip that is about 2 years old. And at that time, it was not optimized for transformers yet. So we haven't optimized for it, yet it can execute it because what is possible is to have, what is special in a transformer, two things. On one hand, you have to be able to do math multiplications or matrix multiplications. So I have data of one layer output, data of another layer output, and they have to be multiplied with each other instead of multiplied with a weight. So it means that if I use this digital or this analog core, the weight data shouldn't come from some stored weight matrix or some stored weight information, but it has to come from the output of the previous layer. This chip can do that, just not as efficient as the other layers, because the output of a layer arrives in the activation memory. To get it now in the weight memory to do my matrix multiplication, it would have to go to my level 2 memory and come back, or go to my level 2 memory and then go in the weight elements of my in-memory compute array. Is possible, but will cost a bit more energy. Second important thing for transformers is that you have normalization layers, which use some annoying mathematics that is not accelerated in this. It's not that you do a simple max pooling, you have to do a bit more complicated post-processing on layer outputs. Now again, we have a CPU, so we can do it. The data is sent here, and then the CPU can operate on it, but it will again cost a bit more energy. So transformer optimized processors will also try to accelerate that effectively in hardware. But I'm very sure, and we affect in Zigzag and Stream, we support transformers already. So we did some studies, and it is very clear that they will also benefit from these heterogeneous data flows. Definitely, because transformers have fully connected layers, they have some matmul layers, they also have a variety of different data flows, which will allow us to exploit this with different, or exploit different data flows across cores. The third and the last question I see here is, what are the drawbacks for heterogeneous SoC in the context of near sensor processing? Well, definitely the drawbacks is that it's extra silicon area, which is good if you use it effectively, but which is a waste if it's just sitting there. As a very tangible or practical example, suppose I'm running only neural networks that needs int8 computations, so 8-bit fixed point computations, then this analog core becomes useless, and then it's just silicon area that goes unused, where I better just have put a bigger digital array. So it's clear that you only benefit from heterogeneous architectures if you are running heterogeneous workloads. And it doesn't have to be that a single workload is super heterogeneous, but that you over time on the same platforms run a variety of workloads, where either every workload itself has many different layers and shapes, or across all your networks, there is quite some variety in layers and shapes. Then a heterogeneous platform is good. If you don't have that, and you have the similar workload all the time, then better just put a simple uniform accelerator. There is some in-between possibility that we do not put, and one of the examples there is the chip I showed you here, voila, on the left. So a kind of intermediate form is that you don't put a fixed single accelerator, but that you put a single accelerator, not a multi-core, but a single one that is reconfigurable, that can hence support a couple different workloads itself. And the benefit is then it never sits idle, because either I use it in that mode or I use it in that mode. The downside is that you hence have a lot of extra multiplexers and switches in your data path to support all these different modes, which makes the accelerator inherently a bit less efficient. So it's going to be overhead as well. So it's one big trade-off space, and what's most efficient depends a lot on the mixture of workloads you're planning to run. Voila. So, okay, good. I'm happy I was able to answer some questions from Hashan of Roche. Any other questions? If not, then we'll go to the second part of this lecture, which, oops, let me go to the right slides, which you won't get from me, you won't get from Jan Rabai. He's unfortunately on the plane, but he took good care in making sure that it's a recording tuned especially to this workshop. So it's not a recording that already existed and he just shared it. He specially made it for this class. So for that, I'm going to give the control back to Anoop, who will start to play this. Anoop, are you still there? Hello? Oh, okay, good. Enjoy.
I'm with the faculty of the University of California at Berkeley. And well, hello there. Good morning, good afternoon, depending upon your time zone you're in. Pleasure to meet you all. So my name is Jan Rabai. I'm with the faculty of the University of California at Berkeley. And first of all, I need to apologize to you due to a miscommunication. I'm not capable or able to present this lecture in person or live. Actually, I'm in a plane crossing the Atlantic, going back to California. So that's why we have pre-recorded this lecture. And as a result, you have to basically hold questions till the end of the presentation. So as Professor Verhelst in the first lecture basically indicated, machine learning is getting more and more traction, not only in the data center, but also at the edge and at the extreme edge in wearable devices, the IoT device, and so on and so forth. So what I'm going to do in this second presentation is to focus on the design of coprocessor accelerators for energy efficiency, basically focusing on one particular computational paradigm, which is called high-dimensional computing. And it will be shown that by basically indeed focusing on a particular subdomain, we can improve energy efficiency substantially. So, just to put things a little bit in perspective, the idea that basically using accelerators or basically customized processing for a particular kernel, that would lead to major gains in energy efficiency was already known quite a while. Actually, it dates back to the 1990s. Here's a slide I actually produced in 1997, which shows you that basically by trading off flexibility and efficiency, we can indeed gain substantially in terms of energy efficiency. On one end of the spectrum, you have a general purpose microprocessor, which is very generic and compute virtually anything. But because of the layers of abstraction that exist, basically has a penalty in efficiency. Now, to improve on that, we can actually dedicate or customize the data path of that processor to basically execute certain kernels more efficiently. For examples, multiply accumulate for signal processing, then you get a DSP, or a complete multiply, matrix multiply for like a neural network style applications. The next step, however, is to take that kernel and spawn it off from the main processor to become an independent processing unit, basically focusing and dedicated completely to that particular kernel. So we have satellite processors, accelerators, coprocessors, and so on and so forth. But the most efficient approach is to actually short circuit all the way between function and implementation. Right? Taking the function, implement it completely in a customized fashion, using dedicated logic, doing nothing else than that function, we get the most energy efficient implementation. And already was then shown that this leads to about 3 orders of magnitude in energy efficiency improvements. Now, this slide shows somewhat of the same picture. Again, it's a trade-off between energy efficiency and flexibility. But as you can see, there's a gap. What it shows is there's a gap between general purpose devices, microprocessors, and the intrinsic computational efficiency of silicon, where application and implementation became basically one and the same. And what this picture shows you actually that this gap is not shrinking, but actually is increasing over new generations. And we'll show later that actually now goes up to many orders of magnitude, even more than the 3 orders that I talked before. So this basically shows, as a result, this is showing a trend that basically is now very prevalent in the industry, where we see that architectures have moved from homogeneous realization, where we have the same function like a CPU, like function repeated many times, to more heterogeneous implementation, where you first start adding GPUs and DSPs to your CPU kernel, of course, And finally, where you actually start adding arrays of accelerators dedicated for particular subfunctions. This trend will only continue and get more extreme going forward. We call it extreme heterogeneity, where using not only system on a chip, but system in a package approaches, we can actually bring different memory architectures, different accelerators, optimized for different functions with special interconnect type strategies, and so on and so forth, to lead to a new generation of system implementations with much higher efficiency than what was accomplished before. So that's kind of the general perspective of what we're going to do. So in order to basically make this more concrete, we'll focus on one particular computational paradigm, which is called high-dimensional computing. Now, high-dimensional computing is basically a application domain or a compute domain that is particularly effective for wearable and IoT applications. In other words, for basically realization at the edge or the extreme edge. Now, to basically figure out what it means, let's put some background first. If you look at the world of machine learning basically means that rather than programming an algorithm, a particular module is programmed by basically exposing it to data, and input data and of various nature. And there's many different styles of machine learning. It goes from Bayesian networks, graphical models, belief propagation, support vector machines, to neural nets, and so on and so forth. Now, within that whole world of machine learning, there's one subset which we call neuroinspired, where the basic ideas of the computational paradigm are basically borrowed or basically inspired by what we learn about the human or the animal brain. Examples of that obviously are now very prevalent. Digital neural networks, convolutional neural networks, reservoir computing, and so on and so forth are examples of such. But one style that we're going to basically look particularly at here is the concept of high-dimensional computing. There's one more class of machine learning that is getting a lot of ground, is where we basically start getting not only at the computational model perspective that we're basically inspired, but actually we're starting building hardware that is directly trying to mimic what brain or neural system basically look like. So we have spiking neural network, MEM computing, oscillating networks, and things like that are examples of this. But again, what I'm going to do is focus primarily here on high-dimensional computing. So you probably are not familiar with this concept, so let's basically go a little more in detail. As you know, or may not know, is that the brain basically is a statistical computer. And it's a statistical computer that operates on patterns. Patterns that are formed by various spike trains of neurons or classes of neurons firing in synchronicity, or basically because of phase relationship and so on and so forth. So high-dimensional computing tries to mimic some of that. So it is basically a statistical computational approach that operates on patterns. It is, as a result of that, it's approximate. This is not precise, it is not deterministic, it's based on equivalences, or at least a proximity. The advantage of the approach is that it is very simple. In a sense, it computes in superposition. We'll talk a little bit more about that later. And it supports reasoning and continuous learning. The whole core of the high-dimensional computing approach that makes it really work is the concept of associative memory. The idea that I can store certain patterns and then later on compare new patterns with those stored patterns and see where the best match occurs. Now, this computational concept based on associative memory is something that actually has been inspired actually a computational neuroscientist called Pentti Nerva to basically observe that indeed, if you look at, for instance, parts of the brain, such as the cerebral cortex, you see that basically remembers or resembles very much a memory structure. You look at this picture here, you see that the cerebral cortex has, this is the neural networks that are existing there. You see that it consists of, first of all, decoders on the top, bottom to top type of part. We have word lines, or basically parallel fibers, as they are called, that look like word lines in a memory. We have memory cells, which are called the Purkinje cells, and then finally, basically output buffers, and then even a feedback between output and input. So that inspired basically some of the ideas that are behind high-dimensional computing, and basically were very well described by Penticonerva in his paper in 2009. So what's the basic idea here? So instead of basically using numbers for computation, in high-dimensional computing, we actually use patterns as the basic element of computation. More concretely, we actually using high-dimensional vectors, which mean that we have dimensions of those vectors which are not 2, 3, or 4, but basically very large numbers like 1,000 or more. And we use those high-dimensional vectors as the basic computational symbols. They represent patterns rather than the numbers, and they can be approximate. So they can be compared for similarity, something closeness. Right? So that's the basic idea, that we compute with high-dimensional vectors as patterns. We combine those, we do operations on them, and we basically store them to basically create memory. Now, it turns out that this kind of model of the mathematical properties of high-dimensional spaces and sampling in high-dimensional spaces shows remarkable agreement with behaviors observed in the brain. So let's go a little bit more in detail. Suppose now that I take 2 random vectors consisting of zeros and ones, and I compare them. The way I compare them is by computing their Hamming distance. You XOR them and you count the number of ones, right? So it turns out that when you increase the dimensionality, you actually create more, you increase the orthogonality between those vectors. Suppose I take those 2 vectors and I use only a dimension of 10, you will see that the overall Hamming distance is very much distributed. The higher the dimension, however, you see the more orthogonal your vectors will become. So you go to 10,000, for instance, which is the black curve, you see that virtually any vector you take, the chances that they basically are within a very short distance, or basically or completely orthogonal, is about 99.75%. So this is the basic idea. I take the random vectors and I'm going to use those as basic elements of computing, and I assume they're nearly orthogonal. And this is your basis set. This is where we basically then going to use the basic elements, your alphabet, let's put it that way, which is going to then use to process relations. Now, it turns out that once you query those vectors, when you notice that there's some similarity between vectors, typically it means that you deviate from the near orthogonality, and it infers there's some relation between those vectors. And those relationships, those similarities, is what we're going to use to basically do pattern recognition and so on and so forth. So let me give you an example. An example for the simple domain of text processing. Right? So one example is I want to do language recognition. So I'm getting a piece of text and I want to basically figure out what language it basically is written in. So the way we work with this, we start with an alphabet. Alphabet basically being a set of elements. Basically, in this case, for the language, is going to be 26 characters from A to Z. For each of those characters, which is typically in ASCII would be 8 bits, I'm going to expand that to a large vector of about dimensions of 1,000 to 10,000 of random elements. So basically random selections of ones and minus ones or ones and zeros, right? For instance, here is a particular assignment of random vectors to each of my characters. Now, again, because of the fact that these are very wide vectors, each hypervector is dissimilar to the other ones. So the distance or the product between the two is basically 0. And we fix this assignment. From now on, basically each vector represents a particular character. Now, what we're going to do now is take the information which is in the text to basically create patterns, compute patterns, combine patterns. And we're going to use very simple mathematical operations to do so. The first one is multiplication. We take two vectors and we XOR them together. This leads to a product vector that you can prove to be orthogonal to the two constituent vectors in a sense, and it binds them together. Now, the interesting part is that the multiplication is invertible and preserves the distance. So I can, if I want to, I take this, bind it two elements together, or the two elements that are bound together. By multiplying this with one of the original vectors, I get the other one back out. So I can basically reverse the computation. The second operation we're going to do is permutation. You scramble the vectors. Again, you can imagine that this leads to a vector which is, again, going to be dissimilar. The easiest way to do actually the permutation is just a shift. Shift left, shift right, basically leads to two vectors that are, or an output vector, which is orthogonal to the original one. By the way, this is a unary operation. The third operation is addition or superposition, where we just do a majority element, sum vector. We sum the two vectors together and we binarize the result. This is really good for representing sets, as we will show in a minute. And finally, the final operation is the distance measure, which measures similarity between two vectors. And this can be done using Hamming distance as an example, but you also could use other more complex measures such as cosine distance. The parallel search is to basically measure the closest match. Typically is performed in an associative memory, I already indicated earlier. So let me now show how you can use this to encode my piece of text in a particular language. So suppose I have the word eat, and I'm gonna now combine this into into a trigram that encodes that particular sequence of E, A, and T. The way to do this very simply is to create a sequence, and the sequence can be created by taking the first character, shift it 2 positions, take the second character, shift it 1 position, and then the third character basically not shifted whatsoever, as you can show right here, and multiply those all together, XOR them together, or basically bind them together. So what I'm getting out of that is a new vector, which is basically this multiplication of those 3 elements. And it represents that sequence, that trigram of sequence of characters. Now, if I would do another combination, let's say 8, I will get a different vector that represents that particular sequence. Now, when we now scan that encoder for 3 characters at a time, we scan it through the text. And we add all the trigrams together, basically bundle them together. So we actually get, in the end, one single HD vector, which represents the complete text. And that HD vector, then I will store into my memory, associative memory, for later inference. Now, as I showed you here, I showed you one particular set of data structures, sequence, as well as sequence of 3 characters, and I showed you bundling, addition. But using HD representation, we can do virtually any data structure you can think of. I already said the set is an example. That's the sum of all the trigrams. Sequences we explained as the multiplication of shifted elements of the various elements. But you also can describe graphs like directed graphs, trees, find state machines, p-value pair, 5-hole stacks, you name it. All those data structures can be captured by those primitive operations on basic operating on my orthogonal vectors. So now let's see how this basically works for my language recognition problem. So during the learning, what we do is we take a piece of text from every single language that we basically want to learn about. So in this particular case, we took 1,000 sentences per language for 21 languages, and we only considered letters, so no commas or points or whatever, the spaces were basically ignored. So this was then fed into the encoder that I just described. You basically take trigrams and we add all the trigrams together. In the end, I get a vector, which is a d-dimensional random vector, which represents a particular language, I store this in the associative memory with a particular key. So, well, this language you see here is Dutch. So after training of my 21 languages, I end up with 21 of those 10,000 bit vectors, and I store them in my memory. So this is the learning process. You can see it's very quick. It's a one-shot learning paradigm. I take one piece of text, bingo, combine it, store it in my memory. Now to do inference, to figure out a new piece of text that I don't know what it is, what I do is basically take that input sequence and then feed it into the encoder, like we did before. But instead of storing it in the associative memory, now what I do is measure the distance of this vector with all the vectors that I've stored in my memory. So I try to find the one which has the shortest distance between the two. And then basically this is what I ultimately apply. And you can see that actually for language identification with n-grams of 3, we see we really get very high quality matching, 96.7% accuracy. You can also use this for the hard problem of text categorization. This is email, this is a Word document, this is, you name it, a business document, and so on and so forth. So it shows really working very nicely. But again, this example I use to explain the basic concept of how high-dimensional computing basically works. Now you apply this for many other applications. And here's an example of another application which actually performs space-time sequence classification. And in this particular case, we're looking at biometric signals. Suppose, for instance, that I have an electrode array with 64 sensors that I can put on my arm and use this to measure muscle activity. Now, in this particular case, I get 64 input channels that I then feed into my high-dimensional computing. And now we're going to use that is to basically measure, do gesture recognition, potentially leading to smart prosthesis and so on and so forth. So this is an example of the device, and you can see how using this device can use it to classify and have either my robotic arm perform a particular function given the gesture that you basically indicated. Now, you may ask why you need so many electrodes here. Well, actually, the advantage of having a redundancy in the acquisition array provides us actually with robustness against some variations like movement, long time wear, day to day, and so on and so forth. Now, how would we apply high-dimensional computing to this? So, from the EMG electrode array, what we're getting is the number of signals, time domain signals that we can sample, and basically perform voltage time waveforms. So each of those particular zones provides a particular gesture. So you have the closed gesture, you have another gesture, and so on and so forth. So the way we're going to process this is by, first of all, sample this. We take one particular sampling on time 0, let's say. We get a set of values. What we're going to do is encode that set of values into a spatial representation. We're going to take a high-dimensional representation of each signal, multiply it with the channel number. That basically helps us to basically identify the space where that particular sample was taken. Multiply so you get a set, and we are going to add them together to get a set. As a result, we're going to get one high-dimensional vector 4 times 1. And then we can do this for consequent samples. And again, instead of basically doing spatial encoding, we're now going to do temporal encoding. We have a sequence encoding, which we can do, as we showed before, by basically shifting the values and multiply them together. In this case, we might use a pentagram instead of a trigram. So here's how this computation works. We take a particular channel. You have a value and a name. The value we can quantize and basically map into a high-dimensional vector. For each channel, we also have a specific high-dimensional vector that encodes channel 1, channel 2, channel 3. So we get those 2 high-dimensional vectors, we multiply them together, and we get basically a encoding for that particular channel and its value at time X, approximately. Now, you may ask how you basically translate continuous numbers into high-dimensional vectors? Well, one thing you could use, for instance, as an example, would be to use kind of a thermometer encoding, where you take the two extreme values, let's say the minimum value and the maximum value. You assign random vectors to each of those, random hypervectors, and then we create in between values that are more proximate to one or the other one, depending on the value, if it's closer to the maximum value or to the minimum value. So we combine that and ultimately get kind of a thermometer code that basically where each hypervector basically represents your analog value. So this is basically what I was just explaining, how you encode the continuous values into thermometer code. You basically have a min value, you have a max value, and we basically flip as many bits as basically upon the distance. And as a result of that, you can see a very nice type of correspondence between a particular value and the distance it has to the two extremes. So it's basically a very nice continuous encoder. So next thing we do is, after this mapping of the input data channel plus its value to high-dimensional vectors, we're going to bind them together using multiplication. It's like a key value pair. And since there are n channels, we need to add all of them together. We have to create them into a set. So ultimately, we end up with one hypervector representing that particular time slot. Then we have to encode the sequence, and the sequence encoding is done basically using our sequence mechanism, where you basically do shifts of older vectors and multiply the shifted values together. So you can use trigrams, n-grams, and so on and so forth. And that's what we finally store into the memory. Now, the nice thing about this is, it's very accurate. It works really well. The other advantage that this approach has, let's say, over neural nets and other type of approaches, is that it learns very quickly. Actually, with the first entity, the first time I basically train a gesture, I have my first high-dimensional vector, I actually can start doing inference per se. Obviously, it gets better when I do more, and when I do more sessions and things like that, I get better and better. But overall, you can see that we get very high accuracy levels. And there's very little difference between the first shot and the last shot of the vectors. Now, if you train in one section, however, and you put it in a different context, let's say I change my arm position, where the electrode array for a long period of time, it might shift around, things like that, or I take it off in the evening and put it back on, you will see that obviously things are different and you will get a different result. Accuracy will drop. But combining the new section with the older section, combining that data together and retraining the system very simply with one extra piece of information actually helps us to restore the accuracy to the original numbers. So when you when you adjust the trained data in a new session with incremental learning, we're back to the very nice numbers we had before. So very quick learning, high accuracy, simple computing. So that's the basic idea. Now let's kind of focus a little bit on how would we build a dedicated processor or coprocessor for this particular computation paradigm. It is very different than your traditional computing system, where you have, which is based on binary number representations. This is not the case here. The basic element we can basically use is a pattern represented as a high-dimensional vector. Now, we could try to implement a high-dimensional computing algorithm onto a traditional piece of hardware, such as a GPU or a CPU and so on and so forth. But what you see is, when you do so, we have orders of magnitude differentiation between what the CPU GPU implementation and the ASIC realization. It's not 3 orders of magnitude, it's actually about between 5 or 6 orders of magnitude improvement in efficiency when I basically build an architecture that is really suited for this computation with large vectors. So when you basically would implement a structure like this on CPU or GPU, we have some features of the high-dimensional computing that are underutilized. First of all, we have to fetch very large memories, very large words, very wide vectors from memory. So it basically pays to have a very wide memory access. We also know that the data movement and computation is structured, so randomization is not really needed. We actually can take advantage of that structured access to the information. We are operating on random numbers, so we need somewhere a way to generate those random numbers effectively. The other advantage of the HGC operation is that per dimension in our large vectors, the computations are only on this at the same level. The operations are going to be purely local. There's no ripple things and so on and so forth. Every bit is on its own and has very little relation with the neighboring bit, except when you do a left or a right shift, which is still a nearest neighbor communication. Now, the other advantage we're going to come back to in a minute is about the fact that high dimensional, because it's statistical, has a built-in robustness, a built-in redundancy against failure, something that is not existing in any single microprocessor or GPU. Typically, you take one of those devices and you flip a bit, the machine might crash very badly. This is shown with this picture here. This is again for the language recognition problem, where we've shown that once you start taking the computation and start randomly flipping bits around, so we started putting errors in the distance metrics or vector that we're getting. What you see is that our vector length is about 10,000 in this case. Up to 1,000 errors, there's no impact whatsoever in classification accuracy. Now, when you start to go between 1,000 and 3,000 bits, we're flipping more and more, you start to see a gradual deterioration of the accuracy, but it's not that bad. We still get more than 90% accuracy, even with 3,000 bits flipped around. Then obviously when you get close to 5,000, ultimately all things break loose, because once you're at 5,000, you basically are doing pure random computation. Obviously things don't work anymore. But what it shows is that HD has actually a graceful degradation mechanism, which will help us to translate this into energy efficiency. We actually can reduce the margins we're operating and allow errors to happen at the advantage of maybe becoming more energy efficient. Okay, so that's kind of the concept. Now let's see how this translates into a programmable HD processor. As I said, you take a piece of text I'm going to encode. It consists of characters. There's 26 characters. For each character, I basically store a random vector, a hypervector representing that character. And I store them in my item memory, as we call it. So this is one approach. Another approach actually would be to, instead of storing these hypervectors, I might generate them, for instance, using Cellular Automata or something like that. So take that, then we basically start feeding text in, and we shift the text through and divide it into particular trigrams. We encode the trigram, we shift the value, get the next trigram, and we add all of those things together. And ultimately, you get one language for your trained vector. So this is the encoder, which processes the random vectors using shift, multiply, and add. And then finally, this vector is then stored into the associative memory. And for each of those, a label is assigned, like English, French, Spanish, and so on and so forth. So that's what happens during training. During inference, we compute a new vector and compare it with the existing vector, and we choose the shortest one, this most similar vector. So one of the advantages, there's a couple of advantages here in this architecture. First of all, it's one directional. Data always moves into one direction, so we have no feedback into the structure. So it's a pure data flow machine, a pipeline data flow machine. The other one is that all the computation or the programming for every application is done in the encoder. The item memory and the associative memory are generic blocks, are the same for every application you can imagine. It's only in encoding, and the type of encoding we're using and how we basically do the different steps on our input vectors is where the programming lies. But still, it is a configuration. Once we figure out the application, you set and configure the data path, and you don't have to change it again. So this is not an instruction-based machine. It's a pure data flow machine. So again, now to kind of imagine how we would basically build our encoder. So for this language recognition problem, so you take hello world, let's say we have the E, the L, and the O. We're basically looking at the trigram representing, so we have the H, the EL, and so on and so forth. The first trigram is combining hell. The second one is ELL. The third one is LLO. The shifts and then add them together. So each letter hypervector is permuted twice. So we need two shifts. We need registers, obviously, to store the various values. And we need multiply XOR. It requires at least 3 registers to basically generate your trigram. So you have 3 input values. And ultimately do point-wise division of the text hypervector. So this can easily be implemented by a pipelines data path, where at every stage, we basically get my new letter in, we shift it over one position, and multiply them all together, and basically store them. And multiply them all together, you get your trigram encoding, and then we accumulate this and store, and in the end, binarize it again using a thresholder and store them into our memory. So that's basically the structure that we're building. And you can see how this basically translates, the various elements basically translate in our data path. Now, as I said, finally, in the end, you end up with one language vector. And so in the during the encoding, or basically during the learning, we are just taking computing vector and store them into the memory. We have a language vector, add a label to it. During that's what we do during learning. During inference, we actually take a new vector, which we call the query vector, compare them to all the stored vector, and compute the distance between them. Now, the associative search can be done in many different ways. And how efficient you want to make there's different ways of improving the efficiency of an associative search in the high dimensional space. The first one is purely digital, where you store all your vectors simply in an SRAM. And then when you get a query vector, what you just do is you take the input vector, your query vector, you get one of the you read out one of the stored vectors, you compute the Hamming distance, which is very straightforward. You perform an XOR between the two vectors, and you count the number of ones, which is called the pap count, and you store the distance so that you can compare it over the various vectors that I've stored in my memory. So this is kind of how you would implement this. So you have, if you want to do this in complete parallel, you could actually have an XOR in every cell. And if for every row, I basically provide an XOR. You have a binary counter that counts the number of ones, and then I can do a parallel comparison. That's a very parallel realization. I similarly could do this sequentially, where you do the first vector, you get the distance, you do the second one, compute the distance, you compare the two together, and so on and so forth, and ultimately you find the closest match. So both of them are possible depending upon the performance you want to get, but also about energy efficiency. I actually can bring this into a complete in-memory compute type of realization. So that's kind of the basic concepts. Now let's translate this into a real architecture or a real realization. So here's an example of a realization of that particular processor. You recognize all the elements I've been talking about. We have the item memory, we have the encoder, which is the one that is being programmed. So you need a controller or a set of programming bits. And we have the associative memory, which ultimately tells me what the closest match is. So the item memory stores the randomly generated high-dimensional vectors, the encoder performs the computation, and the associative memory computes the distance. Now to implement this and basically exploit all the real good features of high-dimensional computing, we basically need only a very simple compute element, which we call the HLU, the hyperdimensional logical unit, or the single SID DPU, as we call it as well. It performs the following operations. XOR is multiply. So multiply, we have permute, which is shift with nearest neighbor. That's a very simple nearest neighbor connection between two cells. We need delay. So there's a register, obviously part of it, the clock register. And then you have permute and multiply. We can combine those things together. So that's our basic cell, basically XOR, permute, or store and forward. Now, to basically translate this into a complete hypervector, we just repeat these 2048 times, or whatever number you want to pick, depending upon the dimension that you basically have chosen for your application. So as you can see here, the distance, the connectivity between the cells are very simple and straightforward. We don't have anything beyond nearest neighbor connections. Now that basically allows us to do one single operation, but if I want to do NSET, I'm going to have to repeat this structure and pipeline in a pipeline format. So it is shown right here. Now to do more complex things, I'm going to repeat each HLU layer n times, depending on how much complexity you want to have, trigrams, n-grams, and so on and so forth. So we have a number of those horizontal layers that are basically connected using multiplexers, so I can program the connectivity to basically perform sets, bundle, and so on and so forth, bind, you name it. The result ultimately gets accumulated, and while we're processing 2D sequence, we accumulate the results, threshold them, and you get a binary vector out. Now, the nice thing about this nearest neighbor connection is also that if I want to actually extend my dimension, let's say I build a chip for a dimension of 2048, and I need something like 10,000, I just can chain a number of chips together and connect them directly at each of the layers. And I get basically a machine that can operate at a dimension which are much wider. So it's very easy to extend the dimensionality. So to show how effective this really is, here's an example of a realization of such a high dimensional binary core. I implemented a 28 nanometer technology from TSMC, voltage, operational voltage 0.9 volt. You can see the various components. On one side here, you have at the top level, we have the item memory, which stores a number of random vectors that are predefined. So we can just use ROM modules to basically store those values. Now, the ROM module that's available in the TSMC library has a limited fan out, so the bandwidth. So in this particular case, it was 128. So we actually put 16 of those memory modules on the die. And then we basically have the first logical encoder stage, the second logical encoder stage, allowing to do basically space-time encoding, and the associative memory. And as I said, the whole structure, it takes about a couple of 4 or 5 million cells, operates at 0.9 volt. The die size is very small, 2.73 millimeters square. Next to that, we show the measurement setup for this device. So we have an FPGA that basically helps us to load the various applications, fetch vectors and input vectors and output vectors into the chip. We also have a number of power management units that allow us to change the supply voltages over the different domains and actually measure very precisely what the current draw is at any point in time. Now, this shows really what the advantages of basically picking a particular dedicated piece of processor for a particular function. This compares the result of this chip that I just showed you with other approaches to implement the EMG hand gesture recognition problem. Spiking neural nets, support vector machines, neural nets, and so on and so forth. And what we notice is indeed we get about orders of magnitude 3 to almost 6 orders of magnitude gain in efficiency by basically dedicating the the processor to one particular computational paradigm. Now you can say, well, that's fine. That basically is comparing with it. What would happen if I just would realize the same function, the high dimensional function, but using different implementation approaches? And again, here, even for HGC data paths that have been published in literature, you've seen that this structure that I just presented here, this pipeline data path, type of architecture is at least a factor of 8 to 10 better than other published approaches for the same problem using high-dimensional computing, but more on different platforms like FPGAs or on using different memory architectures. Now, one last thing I want to point out, which I think is really important, and what brings really this prototype to bear, is that is the robustness of this approach. As I mentioned before, the advantage of HD computing is that it can start basically scaling, introducing errors without impacting accuracy. Now, the way to do that and to measure this is by indeed basically taking the chip and basically start modifying the supply voltage and see what's happened there. Now, we did one thing in the design of this particular chip that basically helps us to support the overscaling perspective in a maximum way. So typically, when you do design a piece of digital hardware, you optimize in such a way that all critical paths pretty much become the same, and that the slack, the timing slack, is minimized. Now, the disadvantage of that approach is once you basically go and overscale your supply voltage, all hell breaks loose and your system fails completely. So we actually did something different here by basically changing the optimization of the logic and basically spreading the setup slack over a much broader band. We have actually a heavy tail band. We have fairly little critical path with zero slack, but you have a lot of them with a large slack. This has the advantage that when we start overscaling, the number of errors is not going to multiply dramatically right away, but it's going to increase gradually, and then ultimately becomes obviously a dynamic failure. Now, to show the impact of that, and we see here the results, measurement results, we see that basically when we start scaling the supply voltage, in this case, we start at about 0.6 volt, and we gradually scale the supply voltage down. What we see is that at high voltage, the accuracy is about 27, is really high, it's about 98.5. Now, once we start scaling the supply voltage, we start seeing on this red curve that gradually the number of errors starts to pick up, right? Around 580 millivolt, we start seeing more and more errors occurring. And once you go down to 560 millivolt, the system fails completely. So that's interesting, but it's more interesting to observe basically what happens with the accuracy. Even when the number of errors gets higher and higher, we see that the accuracy actually doesn't change at all. It's only when we start going to very high number of errors, like 10, 20, 30%, we start seeing some drop in accuracy, but still is darn good. And actually goes all the way down to almost 30, 40% error rate without little impact on the accuracy. And obviously at some point in time, you create that catastrophic point, everything fails, and obviously your application, your accuracy will go to basically zero. So that's one of the biggest advantages of HD computing, and something that will basically help us to basically create, it's a new way basically of creating or augmenting accuracy. Now, that's a more generic thing. So what I'm going to now do is talk a bit more extreme heterogeneity, where we basically say, well, the previous architecture used basically pure CMOS. Is there a way for us to get better performance by using, for instance, new technologies or vastly different architectures to further improve either the density, the size, or the efficiency of high-dimensional computing? And so the next logical step is to think about, maybe we can do something, since it's statistical anyhow, why should I stick to digital computing? Can I not use analog computing? And can I combine these with novel devices such as non-volatile memories to get even better accuracy? So here's an example of an effort that was done at a group at IBM in Zurich, where they basically had a particular memory technology, which is called phase change memory, or PCM, which basically builds on the following concepts. It uses a change in the crystal structure of the memory cell to store zeros and ones and to change the value of the resistivity. So by heating the element, we actually change the material between the electrodes of the memory cell from amorphous to crystalline. And when it gets crystalline, you have better conductivity. When it's amorphous, the resistivity is higher. So this device, it's a non-volatile device. Once you program it, it stays there forever. And what you really program is the resistivity. So I can program this to basically have zeros and ones. And for the rest, basically looks very much like a traditional memory structure. So what's the advantage of PCM? It's actually read latency is darn good. Read efficiency is also very nice. It has very high endurance. You can basically program this thing 10 to the 12 times without too much of a problem. It's very high density, it's non-volatile. So it means I can turn it off when I'm not using the compute device, I turn it off and I can turn it on in no time. So duty cycling is easy. There are some problems. Reading operation is not entirely deterministic. It has noise to it. There's some drift over time. And programming or writing material into the memory is actually expensive. So there's some trade-offs here as well. So you try to minimize the amount of learning, but since most of the time you're not only doing inference, that's not a problem. From a high-dimensional perspective, the nice thing about this is that high-dimensional adds the robustness perspective, and is very, basically the density of the structure is very attractive. So it allows us to store very large vectors with a very high efficiency. So to show you how I can basically now do complete in-memory computing using this PCM structure, here's an example of a realization. So again, we go back to the same architecture as before. A high-dimensional processor has an item memory, have an HD encoder, and an associative memory, all of them with a D vector dimension. So the way the people at IBM implement this, they basically separate the computing into two parts. The first part basically combines the item memory with the encoding into one structure. So we have one memory structure that does item memory plus encoding, and then the second memory structure basically performs the associative memory search. So two blocks that basically are combined. To give you an idea how to do this encoding, the encoding inside the PCM memory, well, suppose I basically take my memory, and in my memory using these, I program the PCM memory cells to store zeros and ones, and for every row basically represents one of the characters of my of my language recognition. So the first row is a vector representing the HD vector for A, B, and Z, and so on and so forth. Total, we have about 26 or 27 times 10,000 devices in my memory cell. So that's purely item memory realization. But how do I now do the encoding? Well, the way the encoding is done is by using the peripheral. What we do is read out one of the cells. For instance, the cell Z. We bring it out to the periphery, store it there in the periphery for a particular point in time. Need to read the next vector and basically combine this with the original vector that's already in there. So the computation is really done in the periphery of the computational entity. So the item memory is encoding conductant states, and the encoding is performed in in-memory read logic, which ones we basically read out and combine, we basically store that into the peripheral element. Now, it is a little bit more complicated than that. If you do a very simple combination of two readout cells, so the in-memory read logic has some problems. Because what we really want to do is compute XOR or XNOR, depending upon the case you look at. If you take the minterms that you get into in the XOR, you basically A and B, or A naught and B naught, right? So that's the problem, because using our current structure, we only have A and B stored. We can OR them together, but we don't have the inverted values. So one way to do this very simply without adding too much memory and logic and so on and so forth is actually to have a second memory that basically stores the complementary values. So instead of storing A, we flip all the bits around and store A bar. So now we can actually do the in-memory encoding. We get the readout, we OR that with the next cell, and so on and so forth. And in the end, to do the XOR, we just need to combine the two together using an OR. So this adds hardware. Obviously, I have another 27,000 cells, but now I can compute both elements of my XOR function effectively and combine them. Now, if you have to go to a more complex structure where you XOR n elements together, that you have to do some optimization or some simplification. If you basically say, well, I'm going to compute every XOR with only 2 minterms, you get a drop of about 7%, and sometimes, or 1% for the language recognition. So that might be acceptable. Similarly, we can do the associative memory inside or inside our PCM memory block, where we take a readout, we compare all the elements of the n stored vectors simultaneously. We compute the distances between what's stored in the input vector and the query vector. We feed it out as an analog signal, feed it into an A to D converter, and then figure out which one the winner is. So this is actually analog in-memory compute. So this is the whole picture here. So we have basically, in this particular case, all computing is done either inside the memory or at the periphery of the memory, and leads to interesting efficiencies and so on and so forth. And again, people at IBM showed indeed that this works very nicely for a set of applications. So this is the summary of this realization. So in-memory computing with PCM and 65 nanometer CMOS peripherals leads to about, they showed that they actually got a 6.6 times energy reduction and 3.8 times area reduction compared to 65 nanometer CMOS. And this is just the first glance at this. I think this basically opens the door for many interesting new realizations. So finally, looking forward into the future, the concept of AG processing with its resistance against variability, errors, and things like that shows that it's an ideal candidate for computing using the emerging nano devices. So in an effort to demonstrate that, together with research at Stanford, we actually implemented a high-dimensional processor, at least a core of it, not a complete complex type system, by combining carbon nanotubes and RAM memory cells. And then stack those things on top of each other in a purely 3D integrated fashion. So this is the basic structure of the implementation of this high AG language processor using nanotechnologies. The classifier is based on the associative memory, is implemented using RAM. And the random vectors actually were not generated by storing, but basically exploiting some of the variability which is inherent in the technology. Actually, in this particular case, inputs were encoded as a time domain, and the different characters were basically determined by the phase of the particular value. So we use phase encoding to basically represent the different characters, and we repeat this about n times, obviously. Now, to basically encode the randomness of this encoding, we actually, as I said, we combined CN FETs, carbon nanotube FETs, with RM to basically create a maximum noise, a maximum distribution, basically white type of selectivity. So random HD projection using RM and CNET variations, accumulation using RM gradual reset, and then associative memory implemented RM, all combined in a single technology stacked on top of each other. You can see here the RM implementation, the CN FETs that are basically on top of it, shows indeed that this opens the door for many wild new thought processes, and again, different ways of doing things that are a lot more efficient than what we can see before. So in conclusion, I think what I've showed you is that by designing coprocessors for selective kernels, we can get orders of magnitude of energy efficiency improvement. Extreme heterogeneity is something that's going to be with us. It's going to be the next energy improvement, the next opportunity in energy improvement. And the bottom line, though, I think I just invite you to be inspired by basically thinking about novel ways of doing and implementing particular function, combining it with novel ways to do computation. Those things together can lead to dramatic improvements that really are needed if you want to get very high efficiency realizations. And that concludes my presentation. At the end of this, I have a number of useful references that you can browse to get more detail about the various things that were discussed in this lecture. Thank you for your attention. Please feel free to send me email if you have any questions. And again, sorry.
Okay, I see some questions that are being asked in the chat. So obviously, Professor Jan Rabai is not online. So I would suggest that you send those questions directly to the chair, or you can even email those questions directly to Jan Rabai. If you send it to us, we will be able to forward those questions to Jan, and then we can take it from there. Once again, thank you for attending this talk. And once again, apologies for a little bit of miscommunications and any hiccups that may have happened while playing the video. I hope you enjoyed it, and see you soon sometime in the near future. Thank you.